This is your presenter Asloob Mudassar, and I am presenting slide number 123 of the course on laser physics. Question is, what parameters are responsible for frequency fluctuations in a laser system? How can the magnitude of frequency fluctuations be determined? Discuss the frequency stability of such systems. Also discuss the theory of a well-known frequency stabilization method. The answer is, there are many factors that are responsible for fluctuations in laser frequency. The factors may be one or more of the followings. Change in the effective optical length of the cavity, LE. So LE, the E subscript stands for effective and L is the length of the cavity. So the change in effective optical length of the cavity LE, where LE is equal to NA times capital L minus small l plus NM into capital L, where small l is the length of the active medium with the refractive index Nm, and the rest of the resonator space is filled with air of refractive index Na, where capital L is the total geometric length of the cavity. Capital Le may change due to changes in Na, that is due to changes in the refractive index of the air surrounding the active medium rod or the active medium region. Temperature drifts or slow pressure changes in the air surrounding the cavity results in a change in L or maybe in refractive index Na. These slow changes, these slow processes may last longer than a second or so and may be referred to as the long-term drifts. So you see that we are now classifying some changes as long-term drifts and some changes as short-term drifts. And this is the first case, this is the first point that where we are referring this to as the long-term drifts. So let me read again. Temperature drifts or slow pressure changes in air surrounding the cavity results in a change in length capital L or may be in the refractive index Na. These slow processes may last longer than a second or so and may be referred to as the long-term drifts. Vibrations of mirrors may lead to changes in cavity length L. Pressure waves within the resonator can modulate refractive index Na. Fluctuations in discharge current results in fluctuations of Nm, that is the refractive index of the active medium. These changes affect Le on fast time scale and may be referred to as the short-term fluctuations. If a laser is pumped optically, here we are talking about optical pumping, not electronic pumping. So if a laser is pumped optically, the variation in pump power results in a change in temperature, leading to change in the refracting index Nm of the active medium and to Le. So the change in temperature will lead to change in Nm and Le. If the active medium is a liquid in the form of a jet flow, air bubbles may be formed in the region exposed to the pump beam and Nm will change. From equation 122.8, that is the equation number 8 from the previous slide, the following equation can be written in the mod form. That is the mod of delta nu L to nu L is approximately equal to delta L over L. That is the mod of delta L over L. And you know that following the definition of thermal expansion, the change in delta L is equal to alpha times L times delta T. So we have written alpha times delta T on the right hand side of equation number 2. where alpha is the thermal expansion coefficient of the material within the cavity, and the change in temperature in the laser environment changes the laser cavity length by delta L. You see that in previous slide, that is in the slide number 128, 122, we didn't use these mod around these quantities, and then you see that there is a negative sign over there, that is delta nu L over nu L was equal to minus times delta L over L. This negative sign indicates that if delta nu L is positive, that is if the change is positive, then the change in the length of the cavity should be negative, which means that the length of the cavity should be reduced in length. This change in cavity length is categorized as the long-term drift. Slow pressure changes in the cavity changes the length of the air column, keeping the length of the active medium rod constant. The change in the laser frequency is then due to this change in the air column, that is delta nu L over nu L, where nu L is actually the frequency at which the laser is operating. So that's why we have designated as nu L. L stands for laser frequency. So this is the frequency at which the laser is operating, and the ratio of delta nu L, since nu is a positive quantity, we have taken it outside the mod sign. So delta nu L over nu L is equal to delta Na, which is the change in the refractive index of the air, the mod of that change divided by Na, and then multiplied by C over 2Le, and C over 2 times L minus L. That can be written as Na minus 1 into Le minus Le into L. Okay. So here we have shown that delta Na over Na is equal to C times C divided by 2Le, and then C divided by 2Le minus 1 is equal to Na minus 1 times capital L minus L over Le, where the effective length is determined by Na. L is equal to 1 into L, because we are taking the refractive index of air to be equal to 1, that is equal to capital L. Let us rewrite this equation as. So we can rewrite the above equation in the following form. So let me first of all show you this equation in more detail in appendix, because I have marked this equation with the red, which means that I am going to say something about this equation in the appendix. So this is appendix 1. You see that Le, which is the length of the effective length of the laser cavity, is equal to Na times capital L minus small l plus Nm times small l. This is shown in equation number 1 of this slide, of this presentation. So let's take the derivative of Na with respect to capital L. Then you see that we have this equation. So I am taking the derivative of this equation with respect to capital L. And then you know that I am going to change dNA by delta Na and dL by delta L. So making these changes, I have the following equation, that is delta Na over Na is equal to minus delta L over capital L minus small l. And then you can take the mod on both sides, which is shown over here. That is a mod of delta Na over Na is equal to mod of delta L over Le. So you see that I am introducing Le in the denominator, as well as I am introducing L in the numerator in the previous equation, that is in this equation. So you can see, and then you can solve this equation, and then you see that I have written this equation over here again, but here I have introduced the value of delta L over LE from our previous equation. So introducing that this equation, that is a mod of delta L over LE, this term is being changed in terms of the ratio of frequencies, that is the mod of delta nu L over nu L. And the rest of the quantity is the same, that is the rest of the term is the same, that is LE over capital L minus small l is the same over here. So just I have replaced this ratio with the corresponding ratio in frequency terms from one of the previous equations in the slide that I have shown. So you see that if I solve this equation for delta nu L over nu L, I get this relationship. You can also keep LE over, you can also keep this term which I have shown over here in a different form. You can also keep it as a capital L minus L in the numerator and capital LE in the denominator. So you see that now I am rewriting this equation over here, but I have shown some terms in red and some terms in green. The term in red can be expanded, that is, you can expand delta NA in a series around the value of NA, keeping only the first two terms, and if you divide that by the value of NA, you will get NA minus 1. And this is the same, you see that either you take it from over here, that is capital LE minus L over capital LE. So this is the same term I am taking over here. So just what I am going to do is that I am going to replace this term, that is delta mod of delta NA over NA, by the term NA minus 1. So no more difference. So you see that this is the expression of delta nu L over L in terms of the parameters, that is NA minus 1 multiplied by capital L minus small l over LE. So this is the term that I am using over here. For example, this one. So you see that now in the previous equation that in the appendix I have shown you, I have made one modification over here in the writing equation number 4. And the modification is that I have moved nu L from the denominator from the left hand side on the towards on the right hand side, that is nu L over here is now present on the right hand side of equation number 4. This Na minus 1 is the same term. Now I am introducing small l in the numerator over here and the small l in the denominator over here, so that I can write this factor, that is small l over capital LE, because I am going to make some changes further, by that is I shall introduce some terms to replace small l over capital LE. That's why I have multiplied the numerator by small l and also divided the denominator. In the denominator I have the term small l. Now to express small l over capital LE in terms of the pressure P and the change in pressure delta P, we proceed with the equation. You know that this is a well-known equation that PV is equal to nRT. So if the pressure is changes to a new value P2, you can write this equation as P2V is equal to N into R into T2. So this pressure is going to change with the temperature, whereas the volume of the system remains constant. Now you can find out the change in pressure using these two equations, that is delta P times V is equal to P2 minus P times capital V times equal to N times R times T2 minus T. So I have taken the difference of these two equations, and then I have written the final term as N into R into delta T. So now you see that I can write this equation in further form as, that is I can write this the term that I have shown in bold, that is delta P times V is equal to N times capital R times delta T. In the numerator I have written this equation and I have divided this equation by the terms in blue, that is PV is equal to nRT. So first of all, I have taken the difference of these two equations. Then the resulting equation has been divided by the term, that is by the initial term, that is initial equation, that is PV is equal to nRT. So if you can cancel out some common terms, and then you are left with delta P over P is equal to delta T over T. So you see that here actually we want to express this parameter, that is L over capital LE. We want to relate it with the pressure terms. So what we do is that we can write delta E, that is the change in the length of the effective, that is the change in the effective length of the laser cavity, can be written as alpha times LE times delta T, where alpha is the thermal expansion, is the linear thermal expansion of the material. And the second equation that I can write, that delta E can also be written as alpha times L times T. And this green equation can be solved for delta T, and delta T can be written as 1 over alpha is equal to times delta LE over LE. And this equation in the red can be solved for the temperature T, which is capital T is equal to 1 over alpha times delta LE over L. So you see that, let me show you the derivation of this equation shown in green and shown in the red in the appendix. So let's move to the appendix. For example, to the appendix number 4. I have already introduced this equation. So this was equation number 1 of this slide, that is LE, the effective length of the laser cavity is equal to NA times capital L minus small l plus NM times L. Change in the effective length of the cavity with the change of temperature can be written as delta LE is equal to alpha times LE times delta T. This is the basic definition of the thermal expansion, of the linear thermal expansion. So a linear thermal expansion will change delta LE, and that will correspond to a change in temperature delta T, and to the original length LE, and also proportional to the absorption to the thermal expansion coefficient of the material. So solving this equation for delta T, I have 1 over alpha times delta LE over LE. Now to write down the second equation, assume that the length of the active medium, the original length of the active medium small l was defined at 0 degrees Celsius. So the change in length delta L can be written as delta L is equal to alpha times small l times capital T. Because this delta T can be written as capital T because the initial temperature was equal to 0. And you know that this delta E, which is the change in the length of the active medium, can be associated also with the effective length of the laser cavity. So delta L can be approximated to be equal to delta LE. So replacing the left hand side of the above equation by delta E can be written as delta E is equivalent to alpha times L times capital T. And then solving this equation, that is this equation for the value of temperature, I have capital T is equal to 1 over alpha times delta LE over small l. So I have two relationships, that is delta T has been expressed in this form, and only T has been expressed in this form. So now using these two values, that is delta T and capital T, from the appendix to the equation over here. For example, this one, delta T can be substituted over here, and capital T can be substituted over here from the following these equations. So delta T is equal to this one, and capital T is equal to this. So making substitutions of delta T and T in equation number 5, I obtained the following result. So delta T over T is equal to, this is the value of delta T, and this red is the value of T, and then cancelling the common terms, I have small l over capital L. So delta T over T can be replaced by L over LE, which is shown over here. So L over LE is equal to delta T over capital T is equal to delta P over P. So now you can change, you can replace this term. For example, in the previous term over here, L over capital LE can be replaced by change in temperature over change in pressure over pressure. So I have replaced L over capital LE by delta P over P from equation number 7. So this is the change in laser frequency. That is this is the change this is the mod of the change in the laser frequency is given by equation number 8. It depends upon the original laser frequency nu L. It depends upon the refractive index of the air in the surrounding the active medium rod. It depends upon the change in temperature and also to the original pressure, so the change in pressure and also to the original pressure in the laser cavity. And then it also depends upon the total actual length of the cavity, capital L minus small l, which is the length of the active medium rod. So delta P can be recognized as a slow change in the ambient pressure P, because the change of a pressure is a slow phenomena. So delta P can be recognized as a slow change in the ambient pressure P. Drift in frequency, which is represented by delta nu L. Delta nu L is actually the drift in frequency. Because the laser is operating at a frequency nu L, when the drift in frequency will take place, then we have computed the change in frequency over here. So the drift in frequency to long-term fluctuations can be kept under 1 megahertz provided low expansion materials are used in the design of the laser cavity, and that the change in ambient temperature is kept below 0.01 degrees Celsius, and the assembly is contained in a pressure stabilized chamber. So if we make these changes, we can keep the fluctuations for the long term fluctuations can be kept under 1 megahertz. Now the drift in frequency due to short term fluctuations are difficult to keep under 1 megahertz. Even if vibration isolation platforms are used and the path of the beam within the resonator is well designed. So we are going to discuss further that the drift in frequency due to short-term fluctuations. Now we characterize the magnitude of fluctuations in the laser frequency. The electric field of the output laser beam can be written as E of t, that is the electric field, that is the amplitude of the electric field oscillating within the laser, is E of t is equal to E naught times sine of 2 pi nu L into t plus phi n of t, where nu L is the laser frequency at which the laser is operating sinusoidally, E naught is the amplitude of that oscillations, and phi n is actually the phase fluctuations, also known as phase noise, where nu L is the central frequency and phi n as a function of time is the phase fluctuations, also known as the phase noise. Drift in frequency results in the instantaneous frequency nu of t given by. So you see that this whole term, that is 2 pi nu L into t plus phi n of t, is actually can be written as 2 pi nu t. So this 2 pi nu t, this 2 pi times nu times t is equal to the argument of this function, that is 2 pi nu L times t plus phi n of t. The derivative, the time derivative of this quantity will give you. So while taking the derivative, we are assuming that this frequency nu is constant at an instant of time. So we have the derivative with respect to time of this quantity as given in equation number 9. And we have represented 1 over 2 pi times the derivative of phi n with respect to t has been designated as nu n of t. That is the nu n as a function of time. So we have on the left hand side nu of t, and now we have written is as the function of time. But while taking the derivative, we have assumed that this nu is constant instantaneously at an instant of time. Nu is taken as constant, but in the long term, we shall see that nu also depends upon time. So nu of t as a function of time is equal to nu L, that is the laser frequency, plus nu n of as a nu n as a function of time, where nu n is due to long term or short term fluctuations in the laser cavity, and can be regarded as a frequency noise. So this nu L is the original frequency at which the laser is oscillating, and this nu n of t as a function of time is actually the noise, frequency noise in the laser cavity. This directly determines the line width or equivalently the frequency stability of a laser. So you see that the smaller the value of a nu n as a function of time, the closer this nu of time will be equal to nu L, and the laser frequency will be stabilized. Spectral power, spectral power density of the frequency noise, which we designate as S nu as a function of nu m, can be used to characterize nu as a function of time. So in order to characterize nu as a function of time, we need to find out the spectral power density of the frequency noise, represented by the function s of nu, and as a function of nu m, s nu as a function of nu m, where nu m is the frequency at which phi n of t is modulated. So you see that due to some reasons, this phi, which is the phase noise, could be modulated at some frequency, and that frequency has been represented by nu m. So we need to calculate the spectral power density of the frequency noise, that is S nu as a function of nu m. To measure S nu as a function of nu m, nu n as a function of time is converted to voltage, that is capital Vn as a function of time, using the frequency to voltage converting circuit. And then the power spectrum of Vn of t, that is the power spectrum of the voltage corresponding to the function nu n of t, is measured using the electronic spectrum analyzer. So since you have the electronic signal corresponding to the function nu n of t, this electronic signal can be analyzed electronically, and the electronic spectrum analyzer will give you the power spectrum of this function. If the line is Lorentzian, then according to the Shallow-Towns theory, the spectral power density of the frequency fluctuations is white, which means that constant with the frequency, that is the spectral power density, will stay constant with the frequency, which means that the fluctuations, that is the frequency fluctuations, is white. So white mean constant in intensity, and which means that no variation in frequency, that is constant with the frequency, and this is given by, so we can write this one, that S nu as a function of nu m is equal to delta nu L over pi, where delta nu L is the line width corresponding to the frequency, oscillating frequency nu L, where nu L is the longitudinal mode. When the laser is operating at a longitudinal mode frequency nu L, we have delta nu as the line width of that frequency. Where delta nu L is the line width defined in equation number 8. To achieve a frequency stabilization, the noise spectrum must be reduced, or equivalently, the cavity length is maintained. So if the cavity length is maintained, it means that you are cutting off the noise factors, and the noise spectrum can be reduced. or in principle, the frequency stabilizations can be achieved. To do this, that is to stabilize the cavity length, one of the cavity mirrors is mounted on a piezoelectric transducer, which is fed by an error signal to increment the length of the cavity. So you see that this piezoelectric transducer would be able to move the mirror longitudinally towards or away the second mirror, so that the length of the cavity can in principle be changed very precisely. And for that one, you need to feed an error signal to increment this length of the cavity change. A part of the laser output beam is fed to a highly stable, high resolution frequency discriminator. Now you see that we are talking about how the error signal could be generated. For that one, follow the description. A part of the laser output beam is fed to a highly stable, high resolution frequency discriminator, and the corresponding voltage fluctuations obtained by comparing the fed frequency to the reference frequency appear as the error signal. So you see that we are actually feeding two signals to our frequency discriminator. One is the frequency from the laser and the other is the reference frequency from some other source, which we shall be talking about later. So these two frequencies are fed to the system, and due to a change in frequency, that is when the fed frequency is different from the reference frequency, an error signal is generated. But when the fed frequency is the same as the reference frequency, then the error signal will be zero and no change will be required at the length of the cavity. But you know that when the fed frequency and the error frequency produce an error signal which is positive, then you see that that is delta nu. That is delta nu L is positive. We need to reduce the cavity length by delta L so that we can stabilize the laser parameters. And the reverse is also true. That is, if the error signal is negative, then of course delta L, that is you need to increase the length of the laser cavity delta L so that you can maintain the other parameters and you can make fed frequency equal to the reference frequency so that the zero error signal could be generated. The error signal is zero when the fed frequency and the reference frequency are equal. So you see that an error signal is given to our piezoelectric transducer, which in terms move the mirror on which it is fixed precisely so that the cavity length should be changed in such a way that the parameters the parameters related with the cavity length remains unchanged. That is, the frequency stabilizations could be assured. The frequency stabilization may be based on a high Venus sharp peaked Fabry-Paro interferometer. So this is the one option for the frequency discriminator, that it could be based on a high Venus sharp peaked Fabry-Paro interferometer or a sharp absorption line from an atomic gas contained in a low pressure cell can be used as the reference frequency, which provides more accurate reference. So the reference frequency or more accurate frequency references can be obtained either by using a high Venus sharp Fabry-Paro interferometer or by using a sharp absorption line from an atomic gas contained in a pressure cell. And this latter technique provides more accurate reference. And you see that this reference should generate a frequency equal to nu L. That is the frequency when the laser is operating and no disturbances are present. So this reference frequency should also be equal to the nu L, that is the frequency equal to the central frequency of the laser. To minimize the frequency fluctuations in the Fabry-Paro interferometer, cavity mirrors are designed to have low expansion coefficients. That is, your Fabry interferometer should also have cavity mirrors which are designed to have low expansion coefficients and must be mounted on structures with low thermal coefficients so that the cavity length of the Fabry interferometer should remain unchanged, so that the reference should remain unchanged. That is, the reference signal should not change. That's why we are calling it a reference signal. The parameters of the Fabry FP must also be unaffected by the temperature and the pressure changes, and the system may be provided with the temperature and pressure controls. So if you are using a Fabry interferometer of a high fineness sharp peaked Fabry interferometer, then you see that you need to provide temperature and pressure controls and also suitable use of low thermal coefficient components and mounts, so that you can keep the cavity length of the Fabry interferometer to be stabilized, so that it can produce a reference signal which should also be stabilized with the frequency. The reference frequency should be independent of temperature and pressure changes and the electromagnetic interferences. So you see that it should be independent of temperature, should be independent of pressure changes, and it should also be independent of the electromagnetic interferences. And it should be highly reproducible. That is, the reference frequency should be highly reproducible. That is, the reference frequency should be maintained under all these conditions. The width of the absorption line is limited by the Doppler broadening when and which can be reduced using Doppler-free nonlinear spectroscopic methods. So you see that if you are using an absorption cell, you can apply the Doppler broadening mechanism. That is a Doppler-free nonlinear spectroscopic methods can be used in order to assure a stable reference frequency signal from the absorption cell. Now you see that more about, we are going to describe a method, modified pound driver frequency stabilization technique is now presented. A small part of the output beam from a laser is first frequency modulated. That is, we have an output, a small part of the output from the laser beam, and that is the first frequency modulated, and then passed through a frequency discriminator. The element that performs modulation produces an output field amplitude that is frequency dependent, and the phase of the output beam after passing through the element also has a frequency dependence. That is, nu is a function of a frequency and phi is also a function of a frequency. So let me read again. A small part of the output beam from a laser is first frequency modulated and then passed through a frequency discriminator. The element that performs modulation produces an output field amplitude that is frequency dependent. So our output, that is our modulation techniques should be such that it produces a field amplitude that is frequency dependent. That is nu, that is E should be a function of a frequency, and the phase of the output beam after passing through the element also has a frequency dependence. That is, through the modulation technique, we are producing two changes in our signal. One is that we are changing the frequency, we are changing the amplitude of the signal as a function of a frequency, as a function of a modulating frequency, and also we are changing the phase of the signal as a function of the modulating frequency. If a Fabry interferometer is used as the modulating element, then the phase phi after passing through it can be found from this expression. And this equation has been given also in slide number 78. That is this is equation number 6 of slide number 78, and here we are labeling it as equation number 11. You see that here is the ET is the electric field of the beam transmitted through the Fabry-Pérot interferometer, and we have shown here the amplitude square of this quantity, and on the right hand side this is the E naught, that is the amplitude square of E naught quantity, and this E naught is the electric field of the incident beam on the Fabry-Pérot interferometer. T1 is the amplitude coefficient, amplitude transmission coefficient of mirror 1. T2 is the amplitude coefficient, transmission coefficient of plate number 2 of the Fabry-Pérot interferometer. R1 is the amplitude transmit, is the amplitude reflection of plate 1. R2 is the amplitude reflection of plate 2. And cos and phi is the phase that is produced with respect to the incident beam when the beam has emerged out from the Fabry-Pérot interferometer. If an absorption cell instead of the Fabry-Pérot interferometer is used, the phase shift is given by phi is equal to k times nl, where this small l, you see that here I am defining these parameters for the absorption cell, which are different from the laser cavity, which I have already defined, where I have used L as the length of the active medium, but here L is the width of the absorption cell and N is the refractive index of the medium contained within the cell. Assuming a Lorentzian line shape of the transition of a frequency nu naught and the transitional width delta nu naught, then the refractive index seen by the resonant frequency nu in terms of the absorption coefficient alpha of the medium is given by. So you see that this is the expression that we are writing for the absorption cell. And we have n refractive index as a function of nu minus nu naught, and that is equal to n naught, the original refractive index which remains unchanged, plus c over 2 pi nu multiplied by nu naught minus nu divided by delta nu naught, and then alpha, which is the absorption coefficient of the medium within the absorption cell, and this alpha is also a function of nu minus nu naught. So you see that nu naught is the resonant frequency of the laser, and nu is the change, and nu is the shift in frequency, and delta nu naught is the line width of the oscillating beam within the absorption cell. Where nu naught is the refractive index seen by the electromagnetic wave at frequency nu naught, that is for nu is equal to nu naught, n is equal to n naught. So you see that in the above equation, if you set the value of nu is equal to nu naught, then this n on the left hand side becomes equal to n naught on the right hand side, because this term will then be equal to 0. The above relationship is modified when the line is inhomogeneous. So you see that this expression for the absorption cell holds for the case of homogeneous line broadening or for the homogeneous case. But if this will be modified when the line is inhomogeneous, phase shifts induced from all atoms are then incorporated, and the transition frequencies nu naught prime of each of the from each of the atom are then distributed according to the function given in slide number 9, equation number 5, which is reproduced over here. So this is actually G star of nu naught prime minus nu naught give you the distribution of frequencies around the central frequency nu naught, and nu naught prime are the frequencies emitted by the different atoms, and this follows, you know, that this is the distribution that is being obeyed by it one by this function, where capital M is the mass of the atom And this distribution has also been discussed in equation number 5 of slide number 49. And you can consult that one there, where the delta nu naught star, that is the width of the central frequency, that is the line width of that one, is equal to by given by this expression labeled as equation number 5, and has also been mentioned in slide number 49, equation number 6. You should consult this equation, that is equation number 6, that is equation number 15 from equation number 6 of slide number 49. The effective refractive index seen by the resonant electromagnetic wave at the frequency nu is then given by the following expression. So you see that the change in effective refractive index is given by n effective is equal to n naught plus c times nt over 2 pi nu, and then the integral of nu naught prime minus nu over delta nu naught, then the sigma h of nu minus nu naught prime, and then multiplied by the function g star of nu naught prime minus nu naught integrated with respect to d nu naught. Where sigma h of nu minus nu naught prime is the homogeneous cross section given by equation number 2 of slide number 40. So in equation number 2, slide number 40, you can see this equation over here, which is the homogeneous cross section. So this effective refractive index is for the case of inhomogeneous line broadening, because here we are using this sigma h for the homogeneous case, and on the left hand side, that is n effective, is actually the effective change in the refractive index due to inhomogeneous line broadening. And this is the homogeneous cross section, where NT is the total ground state population. From the theory presented in slide number 45 or in question number 45, it follows that the absorption coefficient alpha for a plot has been shown over here. That is this. The absorption coefficient that I have just mentioned over here, for example, over here, for example, alpha as a function of nu minus nu naught. This will give you the distribution of absorption coefficient, and the plot of this one versus these frequencies. Here the frequency is nu naught, but you can convert it to omega minus omega naught, and then you can have a plot of this one. The plot of this one is given by this equation, by this graph, which is shown as plot number 1. So you see that when omega is equal to omega naught, you have the absorption is maximum at this frequency, because this is the absorption that is being absorbed by the material of the laser beam. And if you deviate, when your frequency is deviating from the central frequency, then of course the absorption is minimized on both sides. So if we set the phase at the central frequency nu naught or nu naught prime to be 0, that is phi naught is equal to k times nl is equal to 0, it would not change the physics. So you see that the reference for the phase could be set anywhere, because the absolute value of the phase is not important, but of course the change in phase, the relative change in phase is important. So you can also set the phase corresponding to the frequency, where the frequency nu naught is present in the profile. You can set nu naught to be 0 at that frequency. So the phase can be set to 0 at that frequency. The phase shift measured using frequency discriminator is shown in figure number 2. The electric field of the frequency modulated beam can be written as. So you see that earlier we have talked about that we need to first take the signal from the laser beam, a small portion of the signal beam, then we need to pass that one through the through our scheme for frequency modulation. Then the frequency modulated beam is given by this expression, that is E as a function of time is equal to E naught e to the power iota, and then within the parentheses we have omega t plus gamma times the sine of omega mt, where omega m is the modulation frequency and gamma t is the amplitude of a modulated signal. So sine of omega mt is the modulation signal, and it is modulating the input signal with the frequency omega m, and gamma is the amplitude of the modulated signal, and omega of course is the laser frequency, and you are going to modulate this frequency with this factor. So gamma times the sine of omega mt is actually modulating the laser frequency omega. In effect, because the total frequency of the laser in the presence of this modulation frequency will be equal to omega times t plus gamma times sine of omega m times t. And then E of t becomes equal to the frequency of the laser when it is being modulated, where omega m is the modulation frequency and gamma is the amplitude of the modulated signal. So you see that we have said we have given one sentence over here, that is the phase shift measured using the frequency discriminator is given as shown in figure number 2. That is over here. So the caption of the figure is profile of a phase phi versus the frequency omega as measured in the Fabry-Pérot interferometer based or absorption cell based frequency discriminator. So this is the output of the discriminator, giving you the profile of the phase when the frequency changes or when the frequencies deviate from the central frequency omega naught. So the central frequency, location of the central frequency is over here. This is omega naught. And when you deviate, when your frequency, when the laser frequency deviates from the central frequency omega naught, then of course the phase measurement done by the frequency modulator, frequency discriminator is shown over here. You can see that on the left hand side, on the right hand side, the phase is going to be in the negative direction, but on the left hand side of the central frequency omega naught, the frequency is going to be positive. So we can set, so you see that here we have j minus 1, which is the Bessel function over here. J naught, j minus 1 and j plus 1 are the three consecutive values of the Bessel function. So when for the Bessel function j minus 1, we have designated the corresponding phase to be equal to phi minus 1, and at the value of j plus 1, we have corresponding the phase value to be equal to phi plus 1, and at the value of j naught, we have labeled the corresponding phase value to be equal to phi naught. So when j, for the value of j minus 1 to hold, then the value of the frequency should be equal to omega, should be equal to minus omega m, and for to find the location of the j plus 1, we have to have the value of omega to be equal to omega m. And you see that looking at this graph, on the symmetry of the graph, you can say that phi minus 1 is equal to minus, is equal to negative times the value of a phi plus 1. So this is the phase measured by the frequency discriminator when the output, when the Fabry-Pérot interferometer or the absorption cell are used as frequency discriminator, then the output can be obtained in terms of the phase values is given by this expression. For mathematical convenience, expansion of the field in equation number 18. So let me show you equation number 18 first. This is the equation number 18. We cannot process this equation 18 in the present form. So what we are going to do is that For mathematical convenience, expansion of the field in equation number 18 in terms of the Bessel function is required, which is given by. So we have transformed the right hand side of this equation in terms of this expansion. So we have E naught into e to the power iota omega t times this summation sign going from n is equal to minus infinity to plus infinity. Then we have Jn as the Bessel function of order n as a function of gamma, and then we have e to the power iota n times omega mt, where omega m is the frequency of the modulating signal, omega is the frequency of the laser, e of t as a function e as a function of time is the amplitude from the laser output. So we have expressed the above equation, which is modulating the laser beam. We have represented that one in the following form shown in equation number 19. In the expansion, the central frequency and the two sides band at frequency plus minus omega m are important due to their relevance with experimental facts. Thus, the truncated expansion takes the following form. So you see that here the expansion goes from minus infinity to plus infinity. But you know that here we are just considering the three values of n. That is n is equal to minus 1, n is equal to 0, and n is equal to plus 1. Because we are considering only the signal of interest is located at plus minus omega m. That's why we have said that in the expansion, the central frequency and the two side bands, that is omega naught and two sides bands at frequency plus minus omega m, are important due to their relevance with the experimental facts. Thus, the truncated expansion takes the following form by just using only the first three values from the parameter n, that is n is equal to minus 1, n is equal to 0, and then n is equal to plus 1. So that's why we have used this J1. So you see that here we have also used the value that is here we have used that J minus 1 of as a function of gamma is equal to minus times J plus 1 times gamma. And you know that this is what we have represented J plus 1. That is J plus 1. We have represented J minus 1, and we have shown the location of the J naught when the discriminator frequency discriminator determines the profile of the phase. So we have determined their three values over here because we are here incorporating only three Bessel functions, only three functions from the Bessel distribution. That is J plus 1, J minus 1, and J naught. Where we have used j minus 1 as a function of gamma is equal to minus times of j plus 1 as a function of gamma. The field presented by equation number 18 or by equation number 19 is the theoretical field incident on the frequency modulator. And equation number 20, that is this equation, gives you the actual field after passing through the modulator. So this is the actual beam from the modulator. So E of t is actually the electric field from the laser which is being modulated, and this is the actual representation of the signal which passed through the modulator. The field after the frequency discriminator is given by. So you see that this is incident on the discriminator, and the field after the discriminator can be written in the following form. So you see that here we have the inclusion of phi minus 1. Hereby we have included phi naught, and hereby we have included minus phi plus 1, because the discriminator, frequency discriminator, will give you will introduce the measurement of a phase over here with these three terms. Where phi naught, phi minus 1, and phi plus 1 are the phase shifts associated with the carrier wave. when the two side bands at plus minus omega m, with the two side bands at plus minus omega m. So phi naught is associated with the central frequency or the carrier frequency, and phi minus 1 and phi plus 1 are associated with the two side bands located at W is equal to minus omega m and W is equal to plus omega m respectively. The field in equation number 21. Let me show this equation. This is equation number 21. So the field in equation number 21 is then made incident on a photodetector, and the photodetector current corresponding to the signal port at omega is equal to omega naught takes the following form. So you see that when we make this signal shown in equation number 21, this signal to be incident on the photodetector so that we can measure the corresponding current from here, then you see that the corresponding intensity at the port, at the signal port omega is equal to omega m is given by this expression. So let me show you how we can obtain this equation, that is equation number 22 from equation number 1 using appendix. So you see that this is equation number 21. So I have taken the absolute, so I have taken the complex conjugate of both sides of this equation, which is shown over here. You see that J1, I have taken the complex conjugate of J1, J0 and J1 and J plus 1. And I have also replaced iota by minus iota in the terms for the three terms in the bracket. So I have E of t and E star of t. E star means that it is the complex conjugate of E. So you see that for the photodetector you need to multiply the two quantities, because photodetector will not be able to respond to the values of E of t. It will respond to the intensity measurement. So it will respond to the product of E of t multiplied by the complex conjugate of E of t. So the multiplication of these two terms is shown over here. But you know that here I have dropped the conjugate terms over here. If you want to keep the conjugate over here terms also with j, but I have dropped them. And j1 square should be written as j1 mod square. Similarly, j naught square should be written as j naught mod square. Similarly, j1 square should be written as j1 mod square. And at the other places where you have j naught, j1, and here one of them should be a complex conjugate. But I have dropped these sign for the convenience. But you can, but for the accurate results, you need to keep these conjugate signs over here, because the three, for example, here this quantity is in conjugate. This is j naught conjugate. This is j1 conjugate. And you see that the other terms in the previous in the original expressions were real. So you can, when you multiply, for example, if you multiply j1 with this j1 stars, then it becomes j1 mod square. But when you multiply j1 with you should multiply j1 with j naught star. But I have not written star here, but for the actual results you can include this also. So you see that these are the terms that I have written over here when the multiplication is done. So I have also combined those terms having the same values of j. For example, j0 and j1 have been combined over here. Here we have j0 j1. Here we have j0 j1. We have combined. We have written their values over here. So we have selected four terms from the above terms. Why? Because we are using a signal port at omega is equal to omega m. So we are using only the port at which we have omega is equal to omega m. That is our reference frequency. That is our reference frequency is matching with the modulating frequency of the signal. Then we can recover this signal from the as a current signal. So this I is actually the current signal. I stands for current signal at frequency omega m. And due to this one, that we are holding this condition, then we have only selected only the 4 terms over here. Because the other terms, for example, the other terms we have, for example, the blue terms is plus 2 times omega m. That is, the frequency is twice the frequency of omega m. And this port has a filter that filters out the twice the frequency signal. So this signal, which is coming at a frequency 2 times omega m, will be filtered out. Similarly, this signal shown in blue will be filtered out by the electronic signal. And J1 J1 mod square, J0 mod square, J1 mod square shown in red will also be filtered out because these are the DC terms. And so the rest of the terms have been shown over here. And we can combine these two values. For example, we can combine these two negative terms of J0 and J1, and we can also combine the two terms with a positive sign, that is J0 minus and J0 minus terms. These two positive terms can be combined, written in the second row, and the two terms in the first row can also be combined, and we can write them as. So we have written as the real part of this quantity. 2 times the real part, and the 2 we have written outside this bracket. So this should be 2 times the real part of this one. 2 is over here, and we have the real part of this quantity. Because you know that the real part of this quantity is the same. So if you take the real part of e to the power iota omega mt, and if you take the real part of e to the power plus iota omega mt, these two quantities will be the same in as far as the real part are concerned. Similarly, the real part of e to the power iota phi naught minus phi minus 1, and the real part of e to the power minus iota phi naught minus phi minus 1, the real parts will be the same. Similarly, the real parts in the second term will also be the same. So we have written plus real part of this one, because the detector output will be a real part of these quantities. So you can write down the real part outside this main bracket, and then you can include the rest of the terms over here, J0 J1 e to the power iota omega mt, and then you in the curly brackets you can write one term, one phase term from here, the other phase term over here. So this is the current that the electronic circuit will give you as a function of omega m. So you see that I have given you the proof of this equation. So equation 21 has been transformed into equation number 22, and the detail has been covered in the appendix. When omega coincides with the reference frequency omega naught, which is equal to 2 pi nu naught in the discriminator, then phi naught is equal to 0, and phi minus 1 is equal to minus times phi plus 1, and the current and the output current will be equal to 0 only when omega coincides with omega naught. But if omega is different from omega naught, and omega m is much greater than 2 pi times delta nu naught, that is omega m lies much away from the line width of the central frequency, then still you can write phi minus 1 is equal to minus times phi plus 1. Under that condition, the equation number 22 can be written as, that is I of omega m is equal to minus 4 times the absolute square of E naught times J naught into J1 into sine of phi naught into sine of omega mt minus phi 1. So you see that this is the expression that we have written from equation number 22. And the detail of this one is given in the appendix. Let me show you that detail. So this is the equation number 22. So in this equation, you put the value of phi minus 1 is equal to minus times phi plus 1. And you can set these two values equal to minus phi 1. So if you make these changes in equation number 22, you will get this equation. So you see that now I have only two parameters. In this I have three parameters, phi naught, phi minus 1, phi plus 1. So by making this substitution, I have only left with the two parameters, so that is phi naught and phi 1. And then this is a simple geometric manipulation, dividing this by 2 pi and multiplying by dividing this by 2 iota and multiplying with 2 iota, and you are taking this factor common, that is e to the power minus iota phi 1 has been taken common from these two factors. And then you see that you can write write this term as a sine of, so this term can be written as sine of a phi naught. So this expression in the curly bracket is a sine of a phi naught. And this term, which is e to the power iota omega mt minus phi 1, because I have taken e to the power minus iota phi naught common from these two terms, which can be combined with e to the power iota omega mt, and the final result is e to the power iota omega mt minus phi 1. And you know that if you take the real part of this quantity, you have sine of, because you also have iota with this one. The real part, you see that of this one is cos, but when you have iota outside that one, then the real terms becomes, then the sine terms become the real term. So we have sine of omega mt minus phi 1. So I have removed the real part of this term outside this bracket, and I have written all the terms in the real form. And these two which I divided over here, I have also multiplied 2 outside this bracket, so that's why the factor is 4. And this iota, when multiplied with the iota in the expansion of this, then it becomes iota square, and iota square is equal to -1. So we have a minus sign over here. So you see that equation number 20, this is equation number 23. So you see that I have explained how you can write equation number 23 from equation number 22. And equation number 23 and equation number 2 are the same, that is, they are the output from the electronic circuit. But you know that here it is difficult to interpret this one, but the form given in equation number 23 is more easily interpretable. So if omega is greater than omega naught, then phi naught is greater than 0. At omega is equal to omega naught, phi naught is equal to 0. And when omega is less than omega naught, then phi naught is less than 0. The error signal, so this is, you see that is our error signal, which we feed to our piezoelectric transducer mounted on one of the laser cavity mirror in order to maintain the length of the cavity under the other changes that we have been mentioning. The error signal I as a I omega m thus changes the sign and is fed to an electronic feedback system which tries to make omega equal to omega naught. That is the same circuit which is used to control, which is a piezoelectric transducer used to control the length of the laser cavity by moving one of the mirrors towards or away from the other mirror, and thus the frequency stabilization is maintained. So this error signal is fed to the piezoelectric circuit, which maintains the length of the cavity, and then you see that maintains that the omega should be operate at omega naught. The accuracy depends on how precisely the error signal is generated, which in turn depends on the line width of the reference signal used in the discriminator. So it is required that the line width of the reference signal that we feed to the discriminator should be as narrow as possible. The second is that the bandwidth of the electronic feedback system also matters a lot. That is the bandwidth of the signal that we are using in order to do the filtering process should be also as narrow as possible. So you see that under these conditions, we learned that if you maintain the length of the cavity, that is, if you maintained the size of the laser length cavity, you can assure a frequency stabilization. And this is what we have discussed in this lecture. So this is the end of slide number 123.